Welcome back. In this explainer, we're diving into one of the most incredible events in all of human biology, the sheer speed of our vestibular system. We're going to follow the physical force of a simple head movement all the way down to a single ion channel popping open, a process that is, literally, faster than any other sensory event in the human body.
So let's start with the most important number you'll see today. The time it takes for a vestibular hair cell to turn a physical nudge into an electrical signal is less than 10 microseconds. I mean, that's 10 millionths of a second. It's practically instantaneous.
And right away, that speed presents us with a fascinating biological puzzle. It completely blows every known chemical signaling pathway out of the water. Those things take milliseconds to work. So the only possible answer is that this isn't a chemical process at all. It has to be a direct, physical, mechanical event. So how does it work? Well, let's pull back the curtain and explore that mechanical gate. We're going to deconstruct the absolutely beautiful and precise machinery inside the inner ear that makes this microsecond speed of reality. It all kicks off with this structure right here, the hair bundle. And just look at it. The organization is absolutely incredible. You see how the stereocilia are arranged in these perfect rows of graded height, almost like a tiny staircase. This specific geometry is no accident. It is the absolute foundation of the system's sensitivity to motion. Now, linking the very tip of each shorter stereocilium to the side of its taller neighbor is a critical piece of the puzzle, the tip link. The best way to think of this is as a gating spring. Its entire job is to physically pull an ion channel open or let it snap shut, kind of like a rope tied to a tiny trapdoor. What's really interesting is that even when you're perfectly still, there's a baseline level of tension on these tip links. This keeps a small fraction of the ion channels, we're talking maybe 10 to 15%, open at all times. This constant, low-level activity is absolutely crucial because it allows the system to sense movement in both directions. Okay, now watch what happens. When your head moves and this whole bundle gets deflected towards the tallest stereocilium, the tension on that little gating spring, the tip link, cranks up. It yanks that channel open and boom, positively charged potassium and calcium ions flood into the cell, depolarizing it. That's your on signal. And here's the really brilliant part. It works both ways. If the bundle gets pushed in the opposite direction, away from the tallest stereocilium, the tip links go slack. The tension is released, that trapdoor slams shut, and the flow of ions stops. This causes the cell to hyperpolarize. So what you have is this elegant, graded, and bidirectional sensor that responds instantly to physical force. But you know, a mechanical gate is pretty useless without a power source to actually drive ions through it. This brings us to the next critical piece, the completely unique ionic environment of the inner ear. It's just as important as the mechanics themselves. You see, the hair cell kind of lives in two different worlds at the same time. The top part, where all the action is with the stereocilia, is bathed in a fluid called endolymph. But the bottom part of the cell, the basolateral membrane, is sitting in a totally different fluid called paralymph. And believe me, these two fluids could not be more different. The endolymph up top is incredibly rich in potassium, or K+. This creates a massive electrochemical gradient, like a fully charged battery. So the moment those mechanical channels are pulled open, that high concentration of potassium provides an enormous driving force, ensuring an instant, powerful rush of current to depolarize the cell. Okay, so we've got this microsecond mechanical gate that's powered by a unique ionic battery. This is all fascinating stuff, but why does this cellular detail matter so much to us as clinicians? Well, the payoff is huge. It shows up in the speed of the reflexes that we measure every single day. Let's just trace the speed cascade for a second. It's wild. The mechanical gating, less than 10 microseconds. The signal jumping across the synapse to the vestibular nerve, about a millisecond. And the result? The vestibulo-ocular reflex, or VOR, kicks in under 10 milliseconds. It's just a chain reaction of incredible velocity. And this, right here, is where it gets so powerful from a clinical standpoint. Just compare that sub-10 millisecond VOR latency to our visual system. For your brain to see something move, process it, and then command your eyes to track it, that takes over 100 milliseconds. That massive time gap exists for one reason, and one reason only: direct mechanical gating versus slow chemical cascades. So what does that mean for us? It means that speed gap gives us this perfect, clean window into the vestibular system. During a really fast head turn, that first 5 to 15 milliseconds of eye movement is driven entirely by the vestibular system. Your visual system is simply not fast enough to get involved and correct for anything. And that, right there, is the fundamental principle behind the video head impulse test, the VHI. When we see a reduced VOR gain and that telltale catch-up saccade, we are witnessing the direct clinical results of a failure in this rapid mechanical system, whether it's from hair cell loss, ototoxicity, or labyrinthitis. We are measuring the true health of that pure peripheral to brainstem connection.
All right, so let's boil this all down. What are the three big takeaways? First, mechanotransduction is all about direct mechanical gating. It's the only way to get that sub-10 microsecond speed the VOR demands. Second, the tension in the tip link is the signal itself, and it gives us that graded bidirectional response. And third, the potassium-rich endolymph is the system's battery, providing the critical driving force for it all to work.
So we've seen how this incredible mechanical channel opens and closes, but that naturally leads to the next big question. What is it actually made of? What are the specific proteins that assemble to form this remarkable MET channel pore? Next step, I hope you'll join me in video 6, TMC1/TMC2, Identifying the MET pore and its clinical significance. We're going to look at the genetic and biophysical evidence that finally identified the proteins that form this channel and what that discovery means for understanding vestibular function. Understanding this microsecond machinery, it isn't just an academic exercise. It is the absolute foundation of how we diagnose and manage vestibular disorders in the clinic every day. Thanks so much for joining me.
To explore more similar topics regarding dizziness, vertigo, and imbalance, and to get clinician and patient resource materials, visit AustralianDizzinessClinics.com. Please subscribe and leave a rating.